Thank you, Sasha. In some autobiographical notes, Albert Einstein remembered being haunted as a lad by a strange thought. If a man could keep pace with a beam of light, what would he see? Would he observe a wave of electromagnetic energy frozen in place like some glacial swell? It does not seem that something like that can exist, Einstein recalled thinking at the youthful age of 16. There's a stereotype about creative scientists. They're born geniuses whose brains are somehow pre-wired to recognize how nature works. They see a problem, and out of the blue, the answer arrives as if by magic. The science cartoonist Sidney Harris captured this so well in one of his cartoons. He has Einstein standing at the blackboard, and at the top, Einstein has written E equals ma squared. Then he crosses that out. No, E equals mb squared. Crosses that out. Well, of course, reality works far differently. Einstein thought long and hard about that light beam. Creativity did not come easily. He didn't solve the problem until 1905, when he was 26 years old. Einstein's solution was found by thinking outside the box, questioning the unquestionable. He let go of the familiar and found an alternate route. He had this wonderful ability to embrace new ways of thinking. And that often happens in science when a person is young and not yet weighed down by old habits and allegiance to conventional wisdom. A recent experiment even made this point. Two psychologists at North Dakota State University asked a group of undergraduate students to imagine what would they do if school were canceled for the day. Well, the students' responses were pretty bland until they were told to think like 7-year-olds, whereupon the answers became far more original and spontaneous. Likewise, the most creative scientists often retain a childlike curiosity about the world. By thinking outside the box, Einstein concluded that no one can catch up to a light beam, no matter how fast you go, even if you're in a spaceship rocketing away at near light speed. Which seems bizarre until you realize, as Einstein did, that space and time are not absolute, as Isaac Newton had us think. It's, well, relative. Our measurements of length and time alter depending on our motions with respect to one another. The only thing that we will agree on is that light travels at 186,000 miles per second. Moreover, this new idea was backed up by experimental tests. Perhaps creativity in science comes by encouraging heresy. Creative is usually a term applied more to the arts and humanities than to science. In fact, the noun creativity originated fairly late in 1875 to refer solely to poetic imagination, the way in which artists and writers bring new entities into existence. But when applied to scientists, there's one big difference. Scientists can imagine a lot of things, but unlike artists and writers, they are restrained by the rules of the game, the laws of nature that were set into place at the creation of the universe. Their creativity comes into play in the approaches they take in arriving at new theories, which must then be experimentally proven. There is, of course, no precise path, but many roads. Creativity, for instance, can emerge from the mentor-apprentice relationship, which was beautifully rendered by my colleague at MIT, Robert Kanigel, in his book, Apprentice to Genius. In that book, he describes how recognizing a good problem and how to find a solution to it can be handed down from generation to generation of scientists. In Kanigel's book, it involved 4 generations of neuropharmacologists studying drug metabolism and opiate receptors in the brain. creativity was handed down as if genetically from mentor to apprentice. There's further evidence that certain creative habits can be acquired. J.J. Thomson, the discoverer of the electron and a recipient of the Nobel Prize, himself trained 9 Nobel Prize winners, as well as 32 fellows of Great Britain's Royal Society. Well, what are those habits? Louis Pasteur once said, "In the fields of observation, chance favors only the prepared mind." Well, creative scientists are prepared. Legendary discoveries are not lucky breaks, but more like unanticipated detours in well-designed research efforts. Take Alexander Fleming. As the legend goes, a stray bacillium mold lands on a bacteria-filled petri dish in his lab. About to discard the dish, he notices the mold has dissolved the bacterial colonies. Voila, antibiotics. Well, actually, Fleming at first noticed only the mold's mild antiseptic properties. He didn't really clinch that the bacteria were truly being wiped out until further research, after he deliberately cultured the mold. Fleming cast a large net in his lab, experimenting with anything he could find. His creativity came from playing, designing experiments that would yield likely surprises. Creativity can also arise from what looks like to outsiders, like drudge work. Science often involves finding patterns where none are expected, and that comes from gathering lots and lots of data. We've seen that in the Human Genome Project, climate change, Darwin's development of the theory of evolution, even the history of particle physics. Drawing on my own work covering the field of astronomy, a famous example is the work of Henrietta Leavitt. In the 1910s, she was working at the Harvard College Observatory, assigned to examine the myriad photographic plates the observatory was amassing. And she was told to look out for variable stars, stars that regularly vary in their luminosity, brightening, then dimming, then brightening once again. She did her job well. By the time of her death in 1921, she had discovered some 2,400 variable stars, half the number then known to exist. But she went beyond her job description and noticed, out of the hundreds that she was finding, a tiny special group of 25 variables called Cepheids, whose light varied in a specific way. The brighter the star, the slower its period. Tracking the blinks of those variables allowed them to be used as standard candles for gauging distances far out into space. With her deep concentration and focus on her data, Leavitt unearthed astronomy's celestial Rosetta Stone, a means for astronomers to measure distances far beyond the Milky Way. That was not possible before her discovery. It was the tool that allowed Edwin Hubble to discover that the Milky Way was not alone in the universe, but rather just one of billions of other galaxies. More and more creativity, especially in 20th century physics, has been arising from seeking mathematical beauty, as my fellow panelist Lisa probably can attest to far better than I. And it's had its successes. In the first half of the 20th century, physicists were finding a chaotic zoo of elementary particles with their atom smashers. They practically ran out of Greek letters to name them all: lambdas, sigmas, pions. Who ordered that, exclaimed one theorist when the muon, a heavy electron, was identified. Physicists Murray Gell-Mann and George Zweig independently got order out of this chaos through a mathematical breakthrough. Nearly all of those particles were actually composites, each a different combination of smaller, more fundamental particles we now call quarks. The search for mathematical beauty allowed complexity to be replaced by a wondrous simplicity. But can that be carried too far? Some ask that about string theory, which hypothesizes a submicroscopic world that cannot yet be tested directly. What will be interesting to track in the future is whether science is getting hampered in its creativity by its over-specialization, fields getting subdivided further and further into niche specialties. Science has blossomed a millionfold since the 1600s, yet we are not witnessing a millionfold increase in the number of fundamental discoveries. Where are the thousands of Newtons, Darwins, and Einsteins that should now be walking the earth given the astounding explosion in scientific publications? Has science become so bureaucratic that it ends up sabotaging those who would discover? Some believe that new bursts of creative thought will come from interdisciplinary work, chemists talking more to physicists, biologists with mathematicians, so that skills from each discipline will be communicated and exchanged, each teaching the other how to think outside their respective boxes, possibly to think once again like 7-year-olds. Thank you.
And I'd like to say now we're going to hear from Lisa Randall.
Hi there. Welcome on this beautiful day. I can't believe people are inside. I have to say I'm going to be a little bit more creative because I actually didn't prepare remarks. So, so I'm actually going to use some comments that I've drawn together. I'm actually writing another book and was thinking about creativity as one of the subjects. So I'm just going to riff on some of the ideas that were presented just then and talk a little bit about some of the ideas that I've been thinking about. So first of all, I just have to comment on the 7-year-old thing because I just think it's very funny. So when I started out, I grew up in New York. It was the era of the teacher strikes. So actually, my first day of school didn't exist. But I was very disappointed. I didn't do anything creative. I just was very bummed. My older sister, though, was very happy. She already had gone to school and knew that it was good to be out of school for the day. But I think everyone has notions of what creativity is. We think of it in arts differently than we think of it in science. And I think actually it hurts the scientific field that people don't realize sometimes how much creativity is an essential part of what science is. I think I have many friends who say, they didn't really want to do math or science because, they wanted to write or they wanted to do something where they really thought they could be more original and more creative. And I think part of the way we teach science and math sometimes encourages that point of view. And in fact, I say that when I started out, one of the things I did like about science and math, especially growing up in this era of the teacher strike and all that, was that they did have these definite answers and that there was some certainty in it. But of course, what you realize as you become a scientist is that what really it's about are the questions and trying to figure out the answers to things you don't know. And I think that there are just many different types of people who do science, and I think that's one of the things that gets lost. And it's different, and people can be creative in very different ways. They could be mathematically creative. There can be a hard problem that they can come up with a clever way of solving. They can be creative in identifying connections that other people haven't seen. They can be creative in recognizing that something is interesting that everyone else was dismissing, that there was some little inconsistency that might actually be the root to a problem. And I think, when we look at it from after the fact, we tend to say, well, we were thinking in terms of beauty or trying to make things look good. But a lot of the time, it's actually a very messy process when you're doing it. And in fact, it's interesting that you brought up Gelman because actually I was just actually thinking about this topic of truth and beauty in science. And he actually gave a lecture at the TED conference on this very subject. And it's a very glamorous idea to say that scientists can identify what's right by what's beautiful. The problem is that, first of all, as most of you know, we don't all agree on what's beautiful ever in anything. So why would we agree on it in science? And the other problem is that our ideas of what's beautiful actually change over time. And in fact, Gelman's theory is actually a really interesting example because he did have these beautiful organizing principles. He realized that there could be these subunits called quarks, and it could explain this mess, this zoo of particles that was discovered in the 1960s that really people didn't understand why there were all these particles. On the other hand, there was this idea that they were bound together by this force, which is now known as the strong nuclear force. It's also called quantum chromodynamics. So that's actually a very pretty idea ostensibly, except for the fact that it was a strong force. Now, what that meant is that you can't pull these quarks apart. So what we do is quantum field theory and particle physics. So quantum field theory involves putting together quantum mechanics and special relativity so that we can figure out what elementary particles do. Now, the thing is, usually what you can do is you can calculate things, because you can say when they're very far apart, they're not interacting, then they come into some region and they interact, and that's fine. And you can actually systematically calculate it, and you can get it to whatever accuracy you want. But that's not true if these particles are strongly interacting, because in this case, you can't pull them apart. In fact, if you pull them apart, the force gets stronger and stronger. So there were a lot of people that actually thought this was an ugly theory, because it didn't conform to what we had expected a quantum field theory to look like. Now, what's really interesting is after that, people then did a calculation where they showed that although at low energies, which is where we see protons and neutrons bound up, quarks bound up, and all these other strongly interacting particles bound up, we see the strong force is strong. At high energies, the strong force is not strong. In fact, it was called asymptotic freedom. So at high energies, these quarks can be isolated, which means that you can apply all the principles we want to apply, but you can apply them at high energies. So it went from being this beautiful theory to being this theory that seemed ugly because we didn't know what it meant. And now, actually, these are kind of the only theories that we really feel like we truly understand in some ways. So the idea of what is beautiful actually, in some sense, evolved over time. So it's nice when we have some elegant organizing principles, but a lot of the time it's after the fact. After you fully understand something, you can have a nice story that neatly summarizes it, but in between, it can be very messy. And the other kind of amusing thing about that is I was talking to an artist friend who pointed out that really scientists are the only ones who actually look at beauty as the thing they're aspiring to these days. Artists actually don't necessarily. So it's kind of ironic. So I'm just going to, but I think it is important to realize all the different talents that go into being creative for scientists. And you can't uniquely point to one and say this is the person who's going to be the good scientist any more than you can point to one and say this is the person who's going to be the good artist or the good poet. I mean, there are different ways. There are different things that people find appealing, and there are also different ways that people can actually progress towards truth. So I guess a couple of the other things I wanted to mention were some things that do go into it. I'd say are one thing that I do think helps people be creative is the ability to listen to many different points of view. I think a lot of the time, ideas that, if you're going to have a new idea, it's going to be new. It's going to be some idea that either no one thought of, or it's an idea that people were sort of dismissing, or an idea that gets applied in a new context. And so I think people that are willing to be open to new ideas, not every crazy idea, and believe me, there are a lot of crazy ideas out there as well, but people who are willing to listen and maybe say, there could be some element of truth in that. I think also an ability to not necessarily dismiss problems that seem small. Sometimes you have, if you have the big picture in mind, as Marcia pointed out, but even when you see something that seems small, it might be some indication that something's going on. And I think in the world of particle physics, we're in that situation quite often because we really are at the edge of what's possible to experimentally observe. So a lot of our clues will come in the form of things that just seem like small inconsistencies. But these small inconsistencies can give rise to understanding things in a much bigger way. And some of the work that I did with my collaborator Raman Sundram came out somewhat accidentally, but what's interesting about it is that we came at it because we were sort of approaching some old problems, but from a very different perspective, a different orientation. And so we found new solutions to problems in particle physics that people had known about, but we were coming at it from a different perspective. In this case, it involved ideas about gravity. What was sort of interesting about it, though, is that in the process, we ended up discovering new things about gravity that we hadn't anticipated. And we weren't people that did what's called general relativity, Einstein's theory of gravity. We weren't people that were embedded in this way of thinking about things. But so by asking different sorts of questions, we came up with different sorts of solutions that people had missed before. And in fact, one of the things that we discovered, it has to do with an extra dimension of space, but that the extra dimension of space can be infinite. Actually, people had thought was formally proven to be impossible. And that the theory came out and did this. And we hadn't been looking for that, but we noticed it when it happened. And because we didn't actually know, or at least I didn't know that this was proven to be impossible, we kept working on it. And it turned out that it was possible, and it was very interesting to see how the theory actually, it was not a trivial thing that it was able to violate this. I mean, there was a subtlety to it, but it was interesting to see how the theory went about violating it. So I think having in mind, but paying attention and listening not just to other people, but sometimes to what your data says or what your equations say, sometimes gives you new ideas that you wouldn't have anticipated. But since part of the point of this forum is sort of to connect some of the ideas about scientific creativity to other forms of creativity, I thought I'd say a few words about that as well. So I should say, when I wrote my book, Warped Passages, a few years back now, it was really interesting to me because what I hadn't anticipated were sort of the elements of creativity that go into explaining these ideas. I mean, as a teacher, I guess you sort of know it as a professor, but really trying to take this complicated set of ideas and turn it into a linear story where you can sort of follow what are the ideas coming in from many different directions and how they proceed is really a challenging problem. And by the way, trying to make it readable and interesting and anecdotal and sometimes funny and all these other things that go along with it. But really just actually having this logical story. And it was interesting to talk to my friends who are writers and realizing almost the reverse. We think of scientists as very logical and systematic, and sort of the writers as being creative, and of course they have those elements. But writers also, particularly nonfiction writers, also have this incredible, the ones who are very good have an incredible ability to be very logical, to really come up with a linear narrative so that you can read a book, you can turn one page to the next and actually go from not knowing anything about a subject to knowing quite a bit and really feeling like you understand where it's going, where you're coming from. And that's a very logical procedure, one that we often associate with scientists. So it was very interesting to me to talk to my writer friends and realize how many of these almost mathematical, logical elements are going into what they're doing as well. It also was quite interesting to me because I had a very unique opportunity, which I think is one of the reasons I was asked to be in this forum too. After a composer read my book, he asked me to write a libretto for a small opera he wanted to do. And I had never anticipated writing a libretto. But I thought it was a really interesting idea, especially after having tried to put together these ideas in this linear form in a book. And so it was a really unique opportunity for me to work closely with a composer and an artist. And so we could all really see the different ways we were thinking about it. In this point, I was working as a physicist, but also as a writer. So to see the different ways that we all approach the problems. And it was interesting to see how each of us could open up the perspective of the other person. And sometimes not even in the ways that you might have anticipated. But I think one thing that really came through is that for all of us, what creativity involves in some sense is some sort of constrained creativity. If you just could do anything, that could be interesting. But what was interesting for us was that we had a distinct story we wanted to tell with certain constraints. And some of those constraints were just practical constraints, how much you had in your budget, how big your stage was going to be, what things would look like. And some of them are constraints about the story that you wanted to tell and the fact that we all had to do something coherent together. And some aspects of it worked, and probably some aspects of it didn't work perfectly, but it was very interesting to see how each of us worked within the constraints. I mean, I had to write a libretto, which meant that rather than writing in an expository fashion, people actually had to talk to each other sometimes. The composer had to write a story, which meant that he does very electronic, very modern music, quite talented, but he had to really have some sort of story arc in it and to really be able to build that into it. Matthew Ritchie, who was the artist, had to, this I found fascinating because we wanted to represent visually exploring an extra dimension of space, which seemed like, okay, so you just give them more space. But of course, the problem with giving one of the people more space than the other is that the person who doesn't have any space has a very boring existence up on the stage. So how to make that person have space and depth, even though they, in some sense, had to be shown to be more limited. So all of these constraints, I think, gave rise to sort of interesting collaborations and interesting opportunities to work through that. So I found that rather interesting as well. I think but also by doing this, I had other opportunities to talk to people about creativity, and I think it is interesting to see what they say. It's interesting to see what sort of younger people have to say as well. And one of the things that came up was sort of the role of sort of competitions in encouraging or fostering creativity. And I think that's something that we should be thinking about a little bit, because I think science fairs and all these competitions, on the one hand, they really give people the opportunity to really try to do something original and creative. But it was interesting talking to someone who plays the piano, and he was talking about how it gave the incorrect notion that there's one correct way to play a piece. So I think this sort of back and forth between giving people the credentials, but also keeping in mind that they should be doing something original is very important. So these were just some things that I've been thinking about. I think there's just a lot of ideas that permeate the discussions of creativity. I don't think there's any one answer, but I think it is interesting to have this dialogue. So I will just leave it at that.
All right, thank you. So I just want to announce that you're joining us at the Cambridge Forum, and we're continuing our discussion with creativity and science with Lisa Randall and Marcia Bartusiak, and we will continue with questions, and we're going to start with mine. I did want to tell the two of you a story because it's pertinent to using your creativity to write for the general audience. And long ago, I knew a graduate student who did some teaching at a small college, and he decided that in order to test for math competency, he would make up a formula calculating each person's animal magnetism. And the way he worked it out, no matter what it was based on height and weight, but everybody had terrific animal magnetism. And sadly, he found out they weren't math competent. And several hunks came up to him sadly and said, I just know I have animal magnetism. What happened? I scored 0. And on the other hand, some kind of more nerdy people came up and said, I know I don't have it, and I scored 1,000. And so we know the general public tends not to be competent in math, and yet math is the language of physics, cosmology, of science. So how do you two educate and write for the general public without using too much math? Or don't you feel it's necessary to introduce math into it to make it?
I try to avoid equations at all costs. And actually in my books, I do have Einstein's equation of general relativity, but I show it off almost like a sculpture to give people a sense of this great equation. I mean, you hear about it a lot, so you want to see, what does it mean? And actually, it looks deceptively like a simple algebraic equation, and what's hidden within it are actually 10 very gunky partial differential equations that are very difficult to solve. So there's the job of a science writer, or at least I feel my job as a science writer, is not to teach the math, not to teach the science, but what you want to impart is to give people a touch, a sense of an intuitive feel of what that theory has to imply. In fact, funny enough, because I was thinking about this, I brought along some metaphors, and I included something that I had written about that very equation, if I can find it now among my my notes. This is from my book, Einstein's Unfinished Symphony, in which I deal with this idea of how do you describe an equation to your readers? And I wrote about Einstein's equation of general relativity, written in the terse notation of tensor calculus, shorthand for a larger set of equations. The general theory of relativity looks deceptively like a simple algebraic equation. It fits on one line and is the embodiment of mathematical elegance. On the left side are quantities that describe the gravitational field as the geometry of space-time, how much space-time is curved. On the right side is a representation of mass energy and how it is distributed. The equal sign sets up an intimate relationship between these two entities. As Princeton physicist John Archibald Wheeler liked to put it, space-time tells mass how to move, and mass tells space-time how to curve. So you don't have to sit there and say, this is what the G means, this is what the R means, this is what the T means. Ignore the subscripts. You're giving people a sense that what these equations are doing is describing something visual, so that you are coming away with an impression of the physics, impression of the forces involved in nature. And that's, I think, what, especially when dealing with the physical sciences. Lisa did this in word passages. I'd like to plagiarize many of her metaphors. She had a wonderful description of multiple dimensions, and she was trying to answer the question of why aren't we aware of these multiple dimensions? And she compared us to droplets of water on a shower curtain that can't move off of the curtain, can only be confined to it. Even though there is a wide world beyond that shower curtain, we're confined to our membrane. And I just thought that was a wonderful way of giving us a feel. But her book was filled with such metaphors, and I think that really is the meat and potatoes of all of us who are attempting to communicate science, is finding those visual representations that give people that feel of the science, as we're not here to educate, but to impart the sense of what science is saying.
So it's interesting, because when I first started writing my book, I actually didn't like the idea of using metaphors and analogies, because I actually found a lot of them when I read annoying. Because sometimes, especially if you read, this is going to be, okay, I should be careful. But sometimes I think that some of the analogies are more complicated than the thing that you actually started out with. And I think, but then I realized, it's just that I didn't like those analogies, and part of what was my creativity opportunity, in fact, one of the few creativity opportunities you have when you write these books, is to come up with creative analogies, and that was kind of fun. And actually, one of the things that I found interesting was that not all analogies even had to be visual. And sometimes it was kind of fun talking about relationships among particles or different generations, and it was kind of fun realizing all these opportunities that are kind of lost for how you could make these analogies, and they're sort of more fun. In answer to the question you asked, though, I think one of the things you can do in science writing is and this is one of the challenges, is to really identify what is the essence of the concept that really underlies the science, underlies the equation. Equation is expressing mathematically and formally something that you believe, or some physical principles at work. And really finding those, and you realize that the ones that you can really explain are the ones you truly understand. There's some things that I still don't really have a good explanation for outside the equation. Why there's a minus sign for time. Why is time different? I don't have a good answer for that one, and I think that's because we really, at some level, don't really understand this that as well as we understand other things, where I felt like you could come up with a sort of conceptual understanding of what's going on. I sort of compromised in word passages because I did have an appendix with equations for people that really wanted to see the equations. The problem was that the person, when they printed it, they didn't get them right, and then they got a lot of the notation wrong, and I said many times the corrections, and unfortunately it got printed in one place and then it printed another, and so they never got corrected. So those equations weren't very useful, and I get all these emails like, did you see that equation? But it was kind of fun to try to think of, what is really the underlying physics. And actually, another funny story about the equation was for this opera. So the composer and the artist really wanted there to be real science in it. That was one of the challenges that we had, to sort of have this world where, rather than just say someone is doing science or someone is doing it, to really have someone who goes out and does science. So they really wanted to see equations. The thing is, for me, but they wanted to see them in this sort of more artistic way, a little bit that you were talking about. And for me, that's not how I see equations. I see them as actually saying something. So it was really funny, because I actually had difficulty doing this. And I actually said to Hector, if you want those equations, you're going to have to pick them out and tell me, and I'll put them into the libretto. And then I got attacked for having too many equations in my libretto. But I just don't see it that way. I just see them as something that actually means something. And it was kind of interesting to see them as projected as this sort of more artistic thing. But it's not just math. The composer wrote his music, and some of it is very modern, and he had his own notation, and he would send us the music to Matthew and me. We would not have any idea what it was saying. So it's just, to understand notation, you have to know how to translate it. And if you don't have that language, then you have to do it in a language that you can understand.
I actually have a question. This is Marcia. I have a question for Lisa. Is Richard Feynman, the theoretical physicist, famously said, I believe, at one point, that if you can't truly explain a scientific concept so that a general audience can understand it, you don't understand it yourself. Working with metaphors with your book, did that in some sense, or was there ever a moment where you got a further clarification, where the metaphor actually helped you understand a concept?
I don't think the metaphors per se did. I think that thinking through some of the ideas to the point where you can present a metaphor occasionally did. But I think the metaphors were just more a fun opportunity. I mean, it's really nice when you find a metaphor that really works, that you can really follow through and explain how things follow, and so that's just very satisfying. But I think just thinking it through to the extent that you can explain it sometimes clarified some of the physics.
I have my most fun, actually, when I'm confronted with trying to find the perfect metaphor. I remember talking about two black holes that were circling one another and about to collide, and I talked of them being two sumo wrestlers in the ring, and you just have fun. It can be just a fun experience, so that part of the creativity is coming up with even humorous metaphors.
And I think also using art for metaphors also hasn't been done a lot. And I think what I guess I really try to do, and it sometimes succeeded, is find things that weren't made up just for the point of being a metaphor, something that people actually did encounter in their daily life, so that it's something that would actually resonate and really create some concept or some thought in someone's mind.
So Lisa, since you wrote a libretto, and I said this before the program, when I saw, Lisa was interviewed by Charlie Rose, and you did a wonderful job of explaining concepts. And so then as I started to read more and more about breaks in the fabric of the universe and places in the universe where the laws of physics, if I'm understanding it correctly, don't hold any longer. Time may not be going forward or backwards. Up may not be up. Okay, but I could see where my imagination could go deeply into science fiction, and I wondered. I know Marcia said she would rather not write fiction, but did you ever consider writing science fiction?
I didn't consider writing. I mean, I think basically when you have a good idea, that's when I start considering. I mean, the reason I ended up writing this libretto was because it was presented, and I thought, that's a really good idea. And I actually didn't know if I would do it, because I didn't know if we'd work well together. I didn't know if I'd be good at it. But I thought this is a really interesting idea, so I just wanted to try it. Mm-hmm. So I personally I'm not someone who grew up reading a lot of science fiction or whatever. I mean, so that hasn't ever been something at the forefront of what I thought I would do. But okay. Who knows?
And then, Marcia, you were a scientist, and then you became a journalist. Is that correct? Or
it was actually the other way around. I have an unusual background. As a child, I was out in the backyard with my telescope, and then on the weekend I would be writing awful imitations of Nancy Drew novels. So, I had this yin and yang starting very early. When I went to college, my undergraduate degree, I actually got a journalism degree because I thought that would solve my problem of all the things I was curious about. I'd be able to go out and write about them all. And I was a journalist for 4 years, a broadcast journalist, in fact. And I kept going more and more doing science stories. My science interests were coming back. And that's when I went back to graduate school and ended up getting a master's degree in physics, dabbled with the thought of continuing on. But when I started going around interviewing all my professors and writing freelance articles for the local paper, I saw the handwriting on the wall. And so I merged the two backgrounds with writing and science, and have had the great fortune to just have the best job in the world for the last 30 years.
What I wondered is, do you keep yourself constrained to areas of science that you really understand, or are you ever captured by neurochemistry, and it may not be what you've understood before, but you have to really grapple with it?
Well, there's always the challenge, and it is fun. It is fun to go into a situation knowing absolutely nothing and being that sort of naive reporter and learning it all and putting it together. But most of my career, I've actually been driven by my passions. I actually had a night fellowship at MIT 15 years ago, in which I went back for a sort of sabbatical, in thinking, oh, gee, I've been writing on physics and astronomy for so long. I think I'll take courses and all these other things to start expanding my horizons. And I took a course on psychology with Steve Pinker. Evolutionary biology with E.O. Wilson, and I loved every minute of it. But I was missing my passion, and I proceeded to take a course in astrophysics along the way, and came out knowing that that's what I wanted to write about. And there are some science writers who are generalists, and others who have immersed themselves, like Lisa is immersing herself in theoretical physics. I immerse myself in covering the fields of astronomy and physics and loving every moment of it, because it gives me the most satisfaction in covering that area that I know, becoming a specialist.
Mm-hmm. And I guess for Lisa, again, maybe I'm misunderstanding, but I feel like if you spend all your time on theoretical considerations, making theories, trying to understand things, proposing how to explain the universe, maybe we'd understand the universe, and yet you take time out to teach. I'm just wondering how you can do that. No, I mean, do you feel like... No, what I mean is, don't you feel like you should be giving the world your brain power instead of teaching?
You want to talk to Harvard about that? It's interesting. I mean, I had been doing science for quite a while. I mean, I didn't just write right away. I mean, and it's something I wouldn't have done in the beginning. I guess at the time I decided to do it, it was part of it was that I liked writing. There were other things that were involved, but I think as you get older, you're more aware maybe of a broader world, and it seemed like interesting to be able to communicate these ideas to a broader world. I don't think that any individual scientist has this responsibility, but I think that there is a gap in communication now between modern science and broader audiences because of specialization, because it is difficult. And so it was fun to think about creative ways to try to explain things. Could you do it? Who knew? But it was an interesting challenge as well. And I think it's true that it's frustrating sometimes, and you wish you could do everything, but it was a different type of thing to do, and it was fun to do at the time. Okay. And it's still fun.
And then, Marcia, I was wondering if you have a sense or an explanation. You both have predecessors in writing: Isaac Asimov, Chet Ramo, Paul Davies, Martin Rees, Carl Sagan, of course. Do you think there's something special or different about the scientists who have the urge to write? Because there's certain ones who do pop out, as great populists in a way. They want people to get it. They want people to be excited about science.
Actually, I think one of the challenges that we have is that, and this isn't to cast aspersion on any of those particular individuals, but I think a lot of the time people who write about science are not necessarily the people who are the most active in the field, and they're not necessarily people. And so, and I think it is difficult to convey, and I think it's sometimes more appealing if you cheat a little bit and make it easier, or talk about ideas that people want to hear about. And I think there are some people that are willing to pander. But what I think is really interesting is that there's a huge audience out there of people that really do want to understand science, that they're just smart people that don't know it, that they really want to understand it. And I think it's good to give them the opportunity to learn something too. And it's not necessarily going to be the massive audience, but it's a smart, intelligent audience that really wants to understand. And I think it's just important and to have a conversation with those people as well.
Mm-hmm. I think I'm going to put in a word for my fellow science writers. I think some of the most compelling science writing being done today is, and there are some good books by scientists, but some of the most compelling science writing is being done by those who are not the scientists, who have backgrounds in journalism, English. Richard Preston has a PhD in English literature and did a wonderful book about astronomy called First Light, went on to do The Hot Zone. And what I think the science writers bring, who aren't the scientists, is a great narrative sense. There's really a renaissance of narrative writing that has always been the case in nonfiction writing, but I think it's coming into play in science writing more and more. Just recently, this book on the immortal life of Henrietta Lacks about the HeLa cells is written by Rebecca Skloot, who is a creative writer, and even adding herself into the mix. She didn't want to, but she realized she became part of the story after researching it for 10 years. I think that's what a writer can bring as opposed to the scientist, is all of the skills of the creative writer, setting the scene, adding the color, bringing, observing in a way that sometimes a scientist might be a little reticent because they're talking about their own community. And it's something that has been attracting me more and more in my writing of late. When I started out, I was all after scoops. Oh, I want the scoop. I want the latest story. And more recently, I've been stepping back. As you get older, you start saying, what does it all mean? And you want to start making assessments. My latest book, The Day We Found the Universe, is taking all of that historic research, which has been out there before, about the birth of modern cosmology, Edwin Hubble and his great discoveries, that we are not the sole galaxy in the universe, that the fact that the universe is expanding, but writing it in such a way that it's a darn good story, as opposed to the textbook version that you usually read.
I did want to ask both of you, and I asked Marcia. I know many people who want to write books, and often they write them at too high a level of complexity, and their editors tell them, bring it down, and then they do, and then they say, bring it down. And I wondered if it really has to be dumbed down, or whether, if it's well done, people will understand. So an example of this is, even though I like his books, is the Mehmet Oz, the cardiologist who's on Oprah, has a series called You. And in the series, he has factoids, he has cartoons, he has puzzles to do, scales to do. And actually, when you finish one of his books, you know a lot. You know a lot about the body, about health. But it's really simple. It's almost cartoon strip level. So I just wondered what you both might think about that. I think it serves a purpose.
I mean, I think there's dumbing down and there's just being clear. And they're not, the easiest way to seem clear is probably to dumb it down so that it's so simple that you're not really saying anything. But that's less challenging than actually trying to say these really difficult ideas in a clear way. And I think for me, that was the challenge and I did rewrite a lot the first time, because I think one of the things that distinguishes probably a lot of creative people is you sort of have a lot of ideas in your head at the same time. And when you're writing, that doesn't work as well. You sort of just want to sort of say everything at once. But part of being clear is to really distill those ideas into some sort of linear narrative and to really figure out what it is. And it doesn't mean taking them all out, but it means taking the time to put them in order and figure out how one follows from the other and what it is that you're really saying, and really seeing what are those buried assumptions that you have that you're assuming everyone else has. So I think there are ways to be clear without necessarily dumbing things down.
Do you want to comment? Or?
Well, what I can add is that you can't, I guess I feel like you can't write for absolutely everyone all ages, all categories of education. I sort of strive for the scientifically interested audience. And I agree with Lisa. It really takes some thought, not a dumbing down, but finding a very clear, precise way of being both accurate but yet inviting. And it takes some thought. And that's, as a professor in the graduate program in science writing at MIT, that's what we're trying to teach our students. Not the dumbing down, but finding the perfect way of saying something that is clear upon first reading.
Okay. So I'd like to open to the audience now. Could you please step up and ask your questions? Hi.
I have a question for Lisa. There's been a lot of talk this evening about metaphors and analogies, but it's mostly been about communicating science, which is really what we've been talking about, writing about it, teaching about it, and so on. And so I wanted to ask you, when you're actually doing science qua science, and not even with the person you work with, but thinking about things yourself, what percentage of the time do you think that you're actually using metaphors as opposed to, every once in a while finding a good metaphor? How intrinsic is it to the work of doing particle physics and superstring kinds of things?
So I'm guessing that the answer you would get would depend on who you asked, actually. So I myself don't think I'm ever thinking metaphors. I think I'm just thinking about what's actually going on. Now, in reality, I might well be thinking in metaphors, but if I am, I'm not even aware of it. It's just we're really trying to piece together what's there. Now, by piecing together what's there, you're going to use the tools at your disposal, the ideas that you're familiar with. But it's very rare that I'll say, this is a situation like this, or at least consciously say that. I mean, I might recognize a connection that comes from somewhere else, and in that might be the closest that I would come to doing that. But it's very rarely just a conscious, let me try to figure out an analogous situation. And there are cases where you do that, but I think even when communicating among scientists, it's about the communication quite often. I mean, there are times when it really probably does help to have a metaphor, but sometimes the metaphors that scientists use it was really funny. I mean, I was listening to a string theorist give a talk, and his metaphor was from, he was describing something relatively simple and straightforward in a supersymmetric theory, which is one type of particle physics theory. And he said, well, it's just like it is in the F theory case, which is like but most people, a much more complicated situation, but it was something that he was deeply embedded in. So for him, that was his metaphor. So sometimes the metaphor is just coming from the science that you're more familiar with, but it's not something that we would really view as a metaphor necessarily.
Yeah, I suspect that most of us who work in some scholarly areas don't use metaphors all the time. And it's interesting. I think it's a bias in the creativity literature to point out those times when you do, because they're more dramatic and they communicate more effectively what's going on.
I think that's right. I think it's, we want to find isolate some simple thing. And I'd say maybe it's true in the sense that occasionally breakthroughs come from taking some idea from one area into another. I don't think we're necessarily doing it as a metaphor per se. We really are taking the underlying idea and applying it. So whether you call it a metaphor or not is less clear to me. So I would agree with you that I think it's presented that way.
Please come up to the mic so we can hear you.
I was wondering, I read this article by a math professor, and he wondered if perhaps secondary school math or science might benefit from being taught more like an art or a shop class, rather than as like a body of knowledge to learn something that would encourage more participation. A lot of subjects in school are sort of, they more mirror what professionally someone would do. Like a history class would involve, reading accounts of things and writing about them as someone would do professionally. Whereas there seems to be a disconnect between science education and what a scientist or a mathematician would actually do. Do you think, what are your thoughts on that?
This is Lisa. I think there is a point to trying to get people to do research at a young age and really find out what science is. I think that's a very nice notion that you've just presented. The problem is that we actually have to have teachers who are capable of doing that, and I think that's actually a big challenge. I think one of the things, I did a Westinghouse Science Talent Search project when I was younger, and I think that's one of the things that science competitions do for people that really are thinking about doing science, I think it's nice. And I think, so I mean, I don't know if it's the best solution, but I think the compromises that come in are having these type of competitions, which I do think give people the opportunity to do science and understand what's likable. There's summer science programs. I think those are really not mentioned as much as they should be. I think summer science and math programs, I went to Hampshire College Summer Studies in Mathematics. I thought it was fantastic. And it was fun, and we got to participate, and we were solving problems, but we were more seeing how, I mean, it was taught a lot by graduate students, some professors, and we got to see how people really think about those kind of questions. So I think that given that we're probably not going to reform the entire educational system, I would like to see more attention paid to promoting. I don't think everyone should have to do a science research project, but people that think they might be interested, it's great to give them the opportunity. I think having these summer programs is really important, and I think they should be supported.
I think it also might be important to bring the narrative stories into play. Science is sometimes treated just like all those equations and formulas, but there's some stories too, and that can that can encourage interest. Joy Hakam has written a whole series of books now to bring the history of science to the elementary and junior high school levels, and I think those sorts of projects can also add to the interest.
Although it's interesting because that's actually one of the subjects that came up in this creativity discussion, and I was basically asked about heroes. And the thing is, I think at some level learning about the science itself is almost more interesting. It was interesting because I didn't necessarily express it well, but someone who did was a pianist also said, sometimes you're more interested in learning the subject, the achievement. You're not necessarily interested in the people per se.
It puts it into context.
But a lot of the times you don't even necessarily like the people. It's really the ideas that you're interested in a lot of the time.
But I think for a certain segment of student, putting it into a narrative way can draw them into the topic.
The history of ideas, I would agree with you.
Yes.
And I think that's true.
I'd like to ask Lisa a question that was actually alluded to by the first speaker. As I recall, Feynman also famously once said that science or physics is creativity in a straitjacket, meaning where the straitjacket is the empirical evidence that has to constrain the theory. Without that straitjacket, becomes difficult to distinguish between physics and mathematics, whereas a mathematician can envision just about anything that can come to his or her imagination. They can study and write up, but physics has to have this empirical verification.
Which is a little constrained too.
Okay, but in the development of string theory, there really has not been that constraint of empirical, the empirical constraint, which is forcing physicists such as yourself to constrain their ideas to that which is verified by empirical data. So, in your opinion, is that a problem, and how long can physics go on this way?
I mean, we would all love for there to be more data, and I think string theorists would love for there to be more data too. But I think you're right that it is a challenge in the absence of data to know which direction to proceed. We're all excited because the Large Hadron Collider is working, and we hope we get some data. But I think from the point of view of string theory, I mean, I think one thing that is clear, it has helped mathematics. I mean, there really has been math that's come out. It's also introduced some ideas that actually were used in some of the ideas that I and my collaborators have used to actually explain things about the universe and even could be tested. So even though string theory itself isn't being tested, it has introduced ideas which can be tested. But I do think it's a real challenge, and I think that, and I can't answer you how long, because I think it's going to depend on how many new ideas come out of it for a while.
Hi. You both emphasized the importance of metaphor and clarity in addressing communication and over-specialization. But the process you describe sounds very cottage industry, individuals working on individual works rather than something more like the scientific literature where there's a community incrementally building a larger accumulation of insight. Your metaphors and the clarity aren't reaching introductory science education material. What could we do collectively to better support the creation of these metaphors and clarity?
I would think if the professors and teachers themselves would use some of the science writing that's out there and bring that to their classroom. I know I've worked with some teachers and professors in that way, that they supplement the textbooks with the additional material so that it's brought into the pool of knowledge. And I think it's been very helpful.
I mean, I do think that to some extent metaphors are kind of individual, and what works for someone doesn't necessarily work for someone else. I think it would be a challenge to figure out which are the ones that should be universally accepted. I mean, there certainly are some that get accepted over time. But part of what we like, actually, in science and math is to not have to have this sort of subjective interpretation. I mean, one of the things that math does is get away from that. And so the challenge would be to maintain that while still getting the concepts through.
I'm not a scientist, but my son is, and he went to Hampshire College, which turned out to be a wonderful experience for him because it was all hands-on, no textbooks. The first assignment was to go out and figure out things, and based on that, he was able to. He now has a PhD in structural geology. My question actually has to do with the, are there ever times in which when you get into collaboration with other people who are attempting to use your metaphors, that it becomes, what's the right word, exploitative or misses your intention? And I'll just tell you the one story for my son. He is also a climber, and he was taken out for a shoot in for a video. And the producers of the video really didn't tell him what was going to be the final version of everything. Rather than he thought it was going to be a scientific thing, he's a structural geologist who's an expert in the Himalayas. He's done field work in the Himalayas. And this particular, I won't mention the television channel that did it, but they approached him with the idea that very good climber, smart kid, had a PhD from Virginia Tech, so he's a capable person. And essentially what happened when it came out was really out of his control. And the final version of what came out sort of turned into more like a video game or highly simplistic interpretation of things with so I was just wondering if you've ever had any experience like that in your collaborations. Maybe that's not something that's happened because you've collaborated with more honorable people than a producer of a television show.
Well, I've never had a collaborative effort quite like that. I've had some I wouldn't say fights, tussles with editors over a particular section of a story, and usually what I'm trying to defend is accuracy and certain style points of whether it's truly my voice. But no, I've never actually had a situation where something was sort of handed over to someone else totally without, and not knowing what's going to happen to it. But I think, Lisa, you said you've had some things happen to you that way.
Yeah, I mean, it does happen. I mean, I've actually turned down various documentaries because you don't have control over what happens. And I think it's important to present the right message. And having creative control is important. I mean, even in this opera, I mean, at some level, the composer's going to do what they want, the artist is going to do, and some of it will be great, and some of it won't be what you had in mind. But I think that's part of what happens when you collaborate. I think scientifically, you usually because you're writing a paper together, I think you usually have to converge to some extent on what it is you're saying and the ideas you're trying to present. Otherwise, the paper goes on for a long time before you actually finish writing it.
I'm wondering whether, instead of thinking in metaphors for the purpose of relating to an unscientific community, whether in a more subtle sense you can use metaphors to help create ideas. Like Wittgenstein often wrote in metaphors because he couldn't communicate in just didactic language or something. So I'm wondering, wouldn't that be a way to facilitate more creative ideas for yourself as a scientist to bring it down to a subtle metaphor, not for the purpose of
From this
communicating?
perspective, I mean, some people might consider mathematics a metaphor. It's not. I mean, it's a tool. But, I mean, it's a way of making precise your ideas and trying to manipulate them and figure out what they really mean and imply.
I think there might be a difference between, say, the physical sciences, which are heavily mathematically based, versus something more in the realm of philosophy and psychology, so that the use of the metaphor in the way you were describing might be applicable to one field and perhaps not so much for another.
That's actually a good point. And I think a lot of, I mean, there have been breakthroughs in biology by recognizing, in some sense, even the sort of perspective. I mean, I don't know that it's even metaphor so much, but just a perspective that goes into a, sort of anthropomorphizing the objects that you're looking at. And I think by changing the perspective, sometimes there have been some interesting insights.
I have to think of a way to better communicate my idea.
Okay.
It's interesting, when I think of creativity, I often think of innovative thought or innovation, and I don't think that word's been used tonight, so it was kind of interesting. But what I wanted to...
Innovation gets used in business.
Aha. Maybe I'm showing bias then.
Technology, engineering is usually where you'll find the innovative word. Yes.
Interesting. So I wanted to ask about, it's been many years since I read it, but the late Thomas Kuhn, you know, he wrote on the structure of scientific revolutions. You talked about competitive nature a little bit with science fairs, and there was also the essential tension, I think, you know, another bit of his works. But he talks about the different phases that kind of a field of study goes through, and it can be turbulent. You can move into an area where there's consensus among scientists, and it's normal science as they progress forward along the same paradigm. Another word that may be business abused, but I would just, do you think that there's different, in earlier, in certain times, problem identification, you know, is important, and then the ability to solve problems that have been identified might be more important? And I mean, they all cut through at any given time, but do you think that in general, different phases, like, it require different creative inputs and a different balance between, you know, creativity versus kind of the normal science?
Yeah, I don't think there's one size fits all here. There are certain arenas, and I'm thinking about some of the stories I've covered, where, you know, working on the periphery, for example, you were mentioning that, where there's a problem over here that not many people are bothering with, but someone has that, not so much creativity, but they have a sense, they have this sort of sixth sense that that's a good problem to look at. And I'm going to look at it and I'm going to follow it through. One example, Vera Rubin, the astronomer Vera Rubin. She was in the thick of quasar research when it was really hot in the 1960s. Everybody was searching for quasars, the farthest quasar, the brightest quasar. And she got sick of it. She said, too much competition, I want out of here. She went off and started looking at a problem that everyone considered absolutely boring. She started measuring how galaxies rotate. Sounds really pretty boring, doesn't it? But she sensed that there was something there that she wanted to look further into. And she spent years gathering galaxy after galaxy, building this whole pool of data. And lo and behold, she discovered that the galaxies were spinning too fast to be explained by Isaac Newton's theory of gravity. And she was the one who really, for the rest of the astronomical community, uncovered the dark matter problem, that there had to be other matter, other mass out there, by working on this problem that everyone else was ignoring. So that's part of creativity also, is, as you mentioned, sensing that there's something there and working on it, not knowing if it's going to lead to anything, but in her case, it did. And now it's one of the most outstanding questions in astronomy, is what is the dark matter?
Chasing those slightest contradictions, right? That you see.
Exactly.
Great.
And having that sense of a good problem. Edwin Hubble decided as a graduate student to focus on nebulae, taking a telescope and going across the sky and photographing every disk nebulae that he could find. And at that time, the really hot topics in astronomy were planets and stars, tracking the motions of stars. Nobody was working. A handful of people were working on nebulae. But he sensed that that was a real fruitful area for exploration, which of course led to some of his discoveries. So that's part of creativity as well, is recognizing a good problem.
Thank you.
I wonder if there are any new problems or opportunities emerging in the new media. You focus most of your comments on books in classrooms, for example, but it seems like there are sort of a revolution of media, and books and magazine readerships and newspapers are sort of in decline. I just wondered if you see new forums for scientific communication emerging in the new media, and if you believe that all communication is becoming conversationalized in the sense that it's becoming more interactive. There seem to be more opportunities for better communication of scientific ideas.
I wouldn't necessarily say better, but I would say different. I think books still play an important role because they force you to put things in a logical progression, which I think is important. I think new media offers an opportunity to allow someone to instantaneously go into depth on a subject. I mean, it's actually funny. I actually was in this awkward situation where I was giving a talk at a conference in January, and half the audience consisted of my peers and physicists. So it was supposed to be, and I was told that it should be, really going into depth in some interesting topics or whatever, being provocative. But then half the audience was people that were just people who were there because they were interested in the subject, so they were not scientists. And it was really funny because actually someone from Google was sitting there and basically could do Wikipedia searches every time I used a word they didn't understand. So it allowed me to give the talk I wanted to give, but they could follow it somewhat. So obviously, there are advantages to being able to access information quickly. And I think there's a lot of times that when you're writing, you wish you could go into more depth, but then there are just all sorts of constraints, like how long will people be interested? Well, how do you keep someone's attention span? How do you turn it into a narrative, which Marcia's referred to several times. So I think that I don't know that, I think we think of it as better because it's new, but I think it's different, and I think there are opportunities we haven't yet really exploited, and I think it's one of the real challenges that publishing faces today, is to figure out how to take advantage of that without losing what they have.
Oh, I'm looking forward to the ebooks where you're incorporating video and audio. My book, Einstein's Unfinished Symphony, talked about the last prediction yet to be nailed, last prediction of general relativity yet to be nailed, and it involves detecting gravitational waves. And we're not going to be able to image this. It happens to be that the waves have the same frequency, thank you, as sound waves. So when they are recorded, they could be played back as sound. And I was wishing that I had some little gadget in my book that I could play these
So it's interesting,
these
because that's true, and
sounds,
people do that, but I feel like I don't learn anything when I hear that sound. It's very amusing, and you tell something, and it sounds good, and it catches your attention, but it doesn't necessarily teach you anything. And I mean, I think that's going to be the challenge, to figure out which are the things that are sort of
But things are just fun. That was just a fun
I agree,
part.
it's fun, but I think what's going to be interesting is, can you keep your attention span? I mean, I know that I am very distracted by things on the web, and I can tell you most of that time is wasted. So, so the question is how you can actually do this in a productive way that's interesting and useful. And I should say, on the other hand, when I was writing, it was great to have the web at my disposal. It meant that I could do things so much more efficiently and learn things and look up references, and especially historical things. So, I mean, it's great, but I think you have to use it wisely.
But Marcia, I had asked Marcia about gravity waves attached to translating it into sound, and Daniel Levitin has written that all of music over time is probably in 6 melodies, and although our molecules can't feel the gravity waves sound, I wondered if there might be some pattern of those waves that ultimately we'll find comes down to make sense of those 6 melodies. So if you attach the gravity waves and the sound you'd have on your CD in your book and Daniel Levitin's book, I think it's kind of an interesting, no?
Maybe disco has those 6 melodies.
All right. One more question, then we have to stop.
Hi, my question is for Dr. Randall. When I think of science, or when I think of creativity, I tend to think of intuition, the intuitive process. And when I think of science, I think of the rational process, which is more analytical, and creative, intuition seems to be some kind of mysterious synthetic process. And I'm just wondering, they do seem to be opposed.
So what I think is that sort of focus and attention is sort of underrated when people discuss these things. I think what happens when someone has intuition, one of the things that happens at least is that someone really is embedded in a subject. You know it. So they've gone through every rational consequence, and so it's so much there that I'm not sure about this, but connections are made perhaps more quickly or in different ways than they would be otherwise. So I think that there's something about just staring at something really hard that your mind will start to do things that you didn't necessarily anticipate. So I think that is probably the way it happens at some level, but this is really a subject more for people that are trying to figure out how your brain works than physicists.
Well, when you're doing your physics, just curious, what sorts of processes do you find most fruitful for making advanced?
Well, it's not clear, but for example, it really was true that the way we discovered there was this possibility of an infinite dimensional space was that we were staring really hard at the equations and figuring out, what if you change this? What if you did this? Just really trying to figure out what it meant. So, but at some point, there's a leap to say, this is what it must mean. But it was after really staring, and then after we did that, we thought, well, that can't make sense. And then you go back and look at it even more, and you say, could this make sense? What about this problem? What about that? So, so you're right, that it is a lot of rational and focused logical deductions, but someone from the outside would say, oh, that was just some intuition that you had about how this was working.
And also, this is Marcia, this is an immense preparation that you're bringing to play here. You're grounded in all of the mathematics that goes into being able to go through those different pathways.
I don't think that's just true for scientists. I think it's true for a composer or an artist that, if you have those skills down, that allows you to be creative in ways that you wouldn't be able to without sort of these deep-rooted talents.
Okay. Thank you, Lisa Randall. Thank you, Marcia Bartusiak.